Good day to you all and welcome to this MoTeC webinar. My name is Dwayne Mitchell and I work in the MoTeC Research and Development Centre in Melbourne, Australia. And the topic for today's webinar is helpful hints on communicating via RS232. Now we're going to cover a fair few topics but in fairly brief terms, so don't be too worried about the number of subjects here. Firstly, we're going to quickly go over a description of what RS232 is and some technicalities about data structure and signal levels and wiring. Then we're going to have a look at how you might set up your PC normally with RS232 and in particular with USB adapters. Then we're going to look at which MoTeC devices use RS232 and what those capabilities are because it varies from device to device. Then we're going to go through just some quick tips on each of our different ECU, dash loggers and our PLM and telemetry systems. And finally we'll have a look at some of the PC tools that we use here at MoTeC for analysis and for helping set up RS232 links. So the question, what is RS232? Firstly, it's a relatively old or legacy type of communications system. More commonly, we use CAN on a lot of our devices now, but RS232 has been around since, not quite sure, since the 1960s, I believe, and it's designed for serial data transmission from point to point. So what that means is that we can only use one transmit device and one receive device, and the data can be communicated from one to the other. It's not a multi-drop system, in other words. Now, RS232 was found on all PCs from the start of the PC era, which was about 1983, up until roughly the introduction of USB, which is a far quicker and more versatile system. However, RS232 is still found on a lot of desktop PCs, very infrequently on laptops these days. Normally, they're called COM ports in PC terminology, and the typical older PC would have one or more of these COM ports on the back. Now, RS232 was designed initially for transmitting data to terminals, again in the early days of data communication, things like teletypes. And so there are two forms of data that are normally carried on this form, on RS232. Either binary data, which is what we would traditionally use in modern sort of parlance, and the other type of data was a form of converting text data, which is called ASCII, which is the American Standard Code for Information Interchange, normally just called ASCII. Now, ASCII is often used for things like text. Typically, it's used for strings and messages like that. But raw binary type data is more typically used for things like, in our case, engine RPM or temperatures and so forth. The two types of data are not generally sent within the same messaging system. It will use one or the other form of data transmission. Now, RS232 data has no control timing. Essentially, it's self-timed. It's asynchronous, which means that it can be transmitted at any time, and each individual chunk of information contains its own timing information. Now, as we said, it's a point-to-point system, and that means that you need a single wire for each direction of data transfer. So we need one transmitter sending to one receiver on a single wire, and if we want that other device to send back, then we need another wire for opposite direction. So typically we only have two devices. Now, RS232 does have the capability of having multiple receive devices and only one transmitter, but this is fairly infrequently used, and certainly it's not used within a MoTeC context. So each of these asynchronous data bytes can be transmitted sequentially, and normally they may take multiple data bytes to form messages. So the messages are a formatted collection of bytes, typically to contain things like multiple values such as revs, throttle, and so forth. But normally a single byte on its own has no implicit meaning. It's usually used as a part of a message. Now, unlike later data systems such as CAN and USB, RS232 has no real sophistication in terms of message formatting or error correction. There's some very basic error correction on a byte-by-byte basis, and that's about it. So normally the RS232 system, if you like, is just merely a way of transferring information from one device to another. How that information is corrected is up to the individual software that's operating on those devices. So in other words, you can't automatically connect two RS232 devices and see data. That they have to share common message formatting and error correction as well as the common speed. RS232 data rates are simply defined in bits per second, which used to be called baud, but is normally now just called BPS. And the original teletype applications ran at very slow speeds, for example, 300 bits per second. And the upper limit of normal RS232 is about 115,000 bits per second. So, of course, compared to things like USB, which is over 10 megabits per second, RS232 would be considered a slow mechanism by modern standards. Okay, so data is transmitted in single byte form, and there may be multiple bytes in each individual message. But the timing is specific to each byte, and each byte must conform to this timing for messages to be composed. Now, the normal data format is known as NRZ, and that means that logic 1 is the idle condition, and then it transitions to a logic 0 when you want to transmit the individual data. But if the line is idle, it is in the logic 1 state. So the receive device is looking at this logic 1 state, and when it sees a transition to the logic 0 state, that defines the start bit. Now you can see in the diagram here, I've just shown 1 byte of data, and what we have is the idle condition, followed by the start bit, followed by our 8 bits of data, which start at the lowest value data and move to the highest value data. So that's LSB, lowest significant bit, to MSB, most significant bit, which is effectively reverse order, if you like. And then we have a stop bit at the end, which returns to the idle position. And that stop bit must be there so that we can separate each byte of RS232 data. Now, it's also optional to have a parity bit just before the stop bit, and parity is a way of doing some very basic error checking on those 8 bits of data. Mostly MoTeC applications don't use parity, but it's normally selectable within applications. Okay, so to reiterate, we start from an idle condition. That start bit tells the receiving device that we're about to see 1 byte of data. Then we get our 8 bits, we possibly get a parity bit, and then the stop bit, which is effectively just a logic 1 again. Now the timing is such that you need at least 1 or 2 stop bits to clearly distinguish between one data byte and the next data byte. And that's the only function of the stop bit. Normally 1, 1.5 or 2 stop bits are defined. So in other words, each of these bits has exactly the same interval or timing, and we use 10, 11 or 12 bits for each byte of data depending on whether we have idle bits and how many stop bits there are. Needless to say, both devices must be set for the same speed because the timing of each of these bits is purely a hardware thing which is set in each of the devices, and if the bit speed is not correct, then the receive device will never be able to distinguish the data from the transmit device. And normally the maximum number of bytes per second, therefore, is the bit per second rate divided by the number of bits in the framed byte. So for example, at 19,200 bits per second, if we use 8 bits of data, 1 start and 1 stop bit, that's 10 bits in total. Then at absolute maximum speed, we would get 1,920 framed bytes per second. So the rough rule of thumb here is that you would divide the bits per second number by 10, and you get the approximate maximum number of bytes you can transmit per second. Now, the way RS232 defines its signal levels is a little bit odd, but it's a standard that is designed to reduce the amount of noise. As each data channel only uses a single wire with reference to ground, there's a fairly large voltage swing on this data line, and in fact the logic 1 or the mark voltage level is actually a negative voltage. It's defined within the range of -3 to -15 volts. Where it is in that range doesn't matter. Normally this voltage range is simply designed to reduce the amount of interference on the data. So a logic 1 or a mark voltage level is -3 to -15. The logic 0 or the space voltage level is a plus voltage, +3 to +15. So normally what we're seeing with data is a swing of between 6 and 30 volts for each time there is a change of logic level from 0 to 1 or vice versa. Now there are also control lines in RS232, and they have the opposite sense to the data line. So therefore an active control voltage is a plus voltage and an inactive control voltage is a minus voltage. Now the reason we have these extra control lines, which are optional, is that we can start or stop data transmission. There are a number of forms in which this can be done. The reason for this, again, is historic, if you like. It's based on the ability of the receive devices to buffer the data. So older IBM PCs, for example, had very small data buffers, and if too much data was transmitted, the receiving device basically couldn't keep up with the amount of data. And so what it would do is it would issue a flow control command, either by sending a data byte or by asserting one of these control lines, and that would stop the transmit device from sending any further data. Now once again, flow control is largely related to how older systems worked and their ability to keep up with data speeds. You'll find on virtually all modern PC systems, including those that use USB adapters, you can run extremely high data rates without flow control because the PCs themselves or the MoTeC devices don't have any issues with data buffering. In other words, they're running 10 to 100 times faster than the original RS232 standard would have expected. However, they are signals that are commonly used. The 4 hardwire signals there: request to send, clear to send, data terminal ready, and data set ready. So each of these signals originates from either the transmit or the receive device, and they indicate to the other device either that it's ready to receive data or that it wants to transmit data, and also the inverse of that for the other device. So that's why we have 4 signals. It isn't necessary to use all 4 of these control signals. In many cases, if you need some form of flow control, you just use the RTS and CTS signals and you leave out the DTR and the DSRs. Now again, because we have frequently had our data transmitted in an ASCII form, there is also an actual ASCII command for, which is called X on X off, and that is a transmitted particular value which tells the other device to stop or start transmitting. Now that X on X off format will only work if you're using ASCII data. Okay, so we'll now have a quick look at the wiring connectors. Firstly, we require 1 wire for each data direction, so that's 1 transmit wire, if you like, 1 receive wire, and 1 ground wire. So the most basic form of RS232 is effectively a 3-wire cable. In most cases there are 2 connectors used, but we normally use the DB9 connector, and you can see a photograph of one of those on the screen. It's a small connector. They're called D connectors because of the shape of the housing, and they contain 9, 15, or 25 or 37 pins. You can get all of your RS232 signals into a 9-pin connector, and that's the one that most MoTeC devices would be seen with. So you can see here, if you have a standard connector and you're going from one device to the other, you need to take the transmit data from one plug and you need to plug that into the receive data pin on the other plug. So that's why you can see there's a little crossover cable, and that means that the pin 3 on the left hand connector goes to pin 2 on the right hand connector, and vice versa. Pin 2, the receive data on the left hand connector, is fed from pin 3 transmit data on the right hand connector. Now virtually every RS232 cable on the planet is wired this way, so if you buy them from a normal electronic store, you'll find that that's the way they are. If you buy a straight through DB9 cable, that will not normally work in an RS232 application, so that's why they're normally sold and labelled as serial cables, and they'll therefore have this crossover wiring as a standard thing. Okay, now, of course, what we're mostly concerned with is PCs communicating with MoTeC devices, and secondly, with MoTeC devices communicating with each other. Now, most MoTeC applications take direct control of the COM port settings, so you don't need to set things like the baud rate or the bits per second. All you need to do is make sure that you have selected the correct COM port. Again, we're using this term COM port. That's the normal definition for a serial port on a PC. Now, the older type PCs that actually had physical COM ports, they always start at COM1, and if there are subsequent numbers, they'll just be COM2, COM3, and so forth. Later PCs, which typically, like laptops, don't actually have physical COM ports, they use a USB port, and then we need a USB adapter. And normally when you plug these in, they install themselves, and they quite often install at very high numbers like COM33, COM34. So these aren't always useful for MoTeC applications. Most of the applications were written at a time when there may have only been maximum of 8 or 9 COM ports. So some of our older MoTeC software requires the COM port range to be COM1 to COM9. So you would normally set that up in your control panel. Okay, so the thing that we're really concerned about in the modern world is using RS232 to USB type adapters. And here we have a picture of the one that we sell. It's manufactured by A10. It's called a UC232A. Now, the reason I'm showing you this is firstly because we know these work with MoTeC devices, and we sell them, but of course they're readily available, so there's no reason you shouldn't just buy one from any high street retailer. The reason some other devices are not recommended is because some of our MoTeC devices use non-standard speeds, and a lot of the USB to RS232 adapters don't support non-standard speeds. So the reason we sell this one and recommend it is that it's been proven to use every speed that we can throw it works at, and it's a relatively cheap device. It's in the vicinity of, say, $20 to $30 Australian, and available everywhere. So if you need to use an adapter, I seriously suggest you either buy one from a MoTeC dealer or buy the same device from another supplier. Now, it's frequently the case when people ring for support help that they say, yes, they've got a USB adapter, and that's the first question we have is, well, what is the manufacturer? If it's not one that we suggest, then it's very difficult for us to give you any further assistance. So just to reiterate, we need to use the low COM port numbers on these adapters. Normally you plug these in and Windows will install them automatically, as long as you have the relevant drivers. In most cases, Windows already contains drivers for virtually every adapter on the planet. So if you need to make changes, you need to go through Device Manager, which is accessed by a control panel. So again, if you buy the MoTeC adapter, it comes with an install disk which includes the drivers, and of course they can be downloaded as well from the A10 website. So you may need to go through that process. It's very straightforward, and of course if you're familiar with USB installations, it's the same as any other device that you plug in that needs installation. Okay, but if you do need to find the device in Device Manager, you go through Control Panel, and you can see there with Windows XP there's a slightly more circuitous way of getting there. In Windows 7 it's just Control Panel and Device Manager. Okay, so when you're looking at Device Manager, the objective is to find this device. It should be, if it's been installed correctly, it should appear under the ports tree. I'll just highlight that down here. Okay, so these are all in alphabetical order when you look at your computer. So you just go down to the ports entry and you click on the little minus button and the plus button. It'll drop down the entire tree, and you can see down here we have our adapter. This is in fact one of those A10 adapters just plugged in, so it's exactly what you would expect to see. Now, if for some reason your adapter is plugged in but it hasn't been properly installed, or the driver is not working correctly, it may not actually appear under this ports tree entry. It may appear somewhere else. Typically there'll be an entry called unknown devices, And in that case it will often have a yellow question mark next to it, and that is an indication to you that the driver has not been properly installed and you need to take measures to do that. It will never communicate with MoTeC devices while it's showing that yellow question mark in a little circle. So that's the thing. If it's not working, you go into into Device Manager, and you find either where it is in the COM port tree or whether it appears somewhere else as an unknown device. Then you click on the device, and you can right-click here on the Update Driver selection, which is the one we've actually got highlighted here, and then it'll take you through the update driver process. In this case, you need to have the location of your driver files handy, whether you downloaded them or got them off the disk that came with our A10 device, and you must point the update driver process to those drivers, and you should be out of trouble. When that happens properly, you will then see this listed here, USB to serial COM port. Okay, now what I mentioned was that we tend to want to use low COM port numbers. If you do an automatic install, there's a high chance it's going to be a very high COM port number, and the reason, as you can see, this is on the typical laptop here, we have a lot of COM ports which have been assigned to things like Bluetooth, to the various wireless applications and so forth, and some of these applications use 3 or 4 COM ports each. So they will be assigned automatically, and they will just chew up all of your low numbered COM ports. So therefore we get this one appearing, and it may end up being COM26 or something like that. So if we need to change the COM port number, we right click on this properties entry, and that will take us through to the menu that allows us to change the COM port number. Okay, so on the left hand side we are looking at the properties for that COM port, and we just click on the port settings tab, which is the one you can see here, and what that shows us is the bits per second and so forth, flow control, and then down the bottom we have this advanced button. So we click on this button here, and then that opens this dialog you can see on the right hand side. Now the first stuff on this part we don't really need to concern ourselves with. Really all we're doing is we're going to modify this COM port number here. So we just click on this drop down, and you can see here that each of these ones that are being used are designated as in use. So you wouldn't normally choose one of them. There would be a clash if you tried to override these. In many cases you can go ahead and do that because you may not be using, for example, your Bluetooth adapter, but of course at some point it's going to give you some grief. So you can scroll up and down, and again what we suggest you do is choose one of the unallocated COM port numbers that's between COM1 and COM9. So in this case we've chosen COM4. Then we just simply click the OK button, and then we have everything we need. Now the speed settings here, whilst they are shown in this properties dialog, the MoTeC device itself will take control of the speed settings. When you run a MoTeC application, all it needs to do is make sure you have the correct COM port assigned, and it will take control of the speed settings for you. Okay, now we're going to take a look at the MoTeC devices which are capable of RS232 communication. So for a start, again, we just remind you that RS232 was certainly a part of our earlier devices. It is less prevalent now. The main reason RS232 is still in common use is because GPS receivers almost exclusively use RS232 as their transmission. There are some GPS receivers that use CAN, but we don't sell any of them. They tend to be very expensive and very high end. So most of your generic GPS received devices use RS232. So we still support that, and it's an added feature in some of our later ACUs where you can get direct GPS receive. Okay, so again, there are a number of things that RS232 might be used for in an interaction between either a PC and a MoTeC device, or between two different MoTeC devices. And the first one you can see in our list is this device setup, and this just refers to how your ECU manager or dash manager program communicates with the MoTeC device. So in the earlier devices such as M4, M48, RS232 is in fact the only way you can communicate with those devices. There are some extra provisos. M48s and some M4s require one of our PCI cables, which is basically a voltage converter. If you look back to the screen where I showed the signal levels, the RS232 signal levels are reverse voltages in a sense, and so we need a PCI adapter for some of our earlier ECUs to produce those voltage levels. Okay, so in other words, to do your setup work on an M4, M48, M8, you must have RS232. M800s do not use RS232 for setup, and neither do M84s, which are our entry-level M800 devices. Now, our early dash loggers, advanced dash loggers and sport dash logger also use RS232 for setup. It's possible with an ADL2, although it's not normally done because we use USB, and it's not possible with ADL3 or SDL3 devices, which use Ethernet exclusively. So there are some of our devices which allow multiple ways of doing setup, either RS232, CAN, or USB, or Ethernet, and some of them will have RS232 only. The other device that must use RS232 for setup is our PLM device, which is our professional lambda meter, and that's the only way you can set that device up. One device I didn't list here is our LTC, which is our later lambda to CAN device, and by its very name we can tell that it uses CAN as its data transmission, and you can't use RS232 on an LTC. Now the other thing, of course, is to get data between MoTeC devices, and so we have a number of possibilities for data exchange. M4s, M48s, M8s, and M800s are all capable of transmitting RS232 data, which can be received by, for example, our dash loggers. An M84 is not capable of doing that, and a PLM is capable. So the majority of our devices will transmit data, which can be then received by a dash logger. In addition, the dash loggers can transmit data as well, so they can exchange data either between themselves and another device, but it is not possible for the ECUs to receive RS232 data from a dash logger, only to transmit it. As I mentioned, the most common current usage for RS232 is for GPS signaling, and our GPS devices all use RS232, and our later ECU models, for example the M800 and the M84, are capable of receiving this GPS data. Our earlier ECUs are not. At this point in time there is no likelihood that they'll be upgraded, so if you have an M4, an M48 or an M8, you cannot receive GPS data into those devices. All of our dash loggers allow you to receive GPS data, and the PLM does not, because it's not a logging device. Okay, now back to interfacing between a PC and a MoTeC device. How do we download our logs? The earlier ECUs, the M4, M48 and the M8, which are all the ones that have RS232 as their principal communication, they also use RS232 to download the logs. As we mentioned, RS232 has a slower transmit rate than some of the later communications protocols, and therefore log downloads are a little bit slower. Our later devices have much faster communications rates. They also tend to have much larger logging memories, but generally speaking the download speed is a lot faster. You can't get logs from an M800 or an M84 via RS232, and you can't get it from an ADL3 or an SDL3. And finally, we use RS232 for telemetry. This is where we can transmit data, for example, from the engine computer back to the pits via a radio link, and most of our devices have been enabled for this type of function. The only ECU that isn't is the M84, but the M4, M48, M8 and M800 family will all transmit RS232 data for our telemetry monitor system, as will our ADL dashes, and of course the PLM won't, because it's not designed for that sort of application. Okay, now we'll go through some more specifics. So with an M4, M48 and M8, as you may recall, we only have set up via RS232 for these devices. In some cases you can directly plug a cable in, and in some cases you need one of our PCI or CIM type cables. Okay, so M4 serial numbers below 3000, i.e. the earlier ones, they need the PCI cable or the CIM module. M4 serial numbers above 3000, which are of course the later ones, they use a standard serial cable. And M48 and M8 devices all need the PCI cable or the CIM module. Now, one of the reasons we have a little bit of frustration with some of these earlier ECUs, again on late model laptops, is that people are still using older versions of our ECU manager software. So we have to stress that if you are going to use these older devices with this blue screen software, you should be using version 6.2 of the ECU manager. So that would either be the M4 V62 or the M48 V62 program. These programs allow you to use COM ports 1 to 9. The older versions of this software, which a lot of people still have version 5, effectively will only work on COM 1. And that's of course because they were written at a time when most PCs had a physical COM port which was COM 1. So if you have an older version, it's critical that you install the later version 6.2. That's going to allow you to select any COM port from 1 to 9. Now, when you first launch these programs, you can hit F5 and that'll allow you to select which COM port you're going to use. And then when you're in these programs, you can, to get to the RS232 settings or the telemetry settings, you go General Setup, Miscellaneous Setup 2. And you can see on this screen here, we have a number of other parameters, but essentially what we're looking at are the telemetry baud rate and the telemetry data set. Okay, so the telemetry baud rate, that is the number which defines the bits per second. If you are in this program and you select that, you'll see a help screen which gives you some extra help on what these numbers mean. If it's a number like 1201, it basically means 1200 baud with one stop bit. And there are a number of other variants as well, such as 19201, which is 19,200 bits per second with one stop bit. The one we've got showing here is the data set, and that's selected at data set 3. Now, the older ECUs have a number of data sets which are not present in the later ECUs. So for practicality's sake, we would suggest you use one of the high numbered data sets, that is to say number 5 or number 7, because these are effectively identical to the way the M800 series data sets function, and that means it's a lot easier to set this stuff up in dashes and so forth. So each of these data sets produces a fairly large message. In some cases it can be 150 bytes or more in length, and these data sets contain all of the relevant data. Once again, if you hit the F1 button when you're in this screen, it'll show you the particular items of data that are transmitted in each of these data sets. But it's fair to say that the most commonly used one is number 5, which is our ADL-logger data set. And in fact, number 7 is probably a better one because it uses better error checking, what we call CRC32 error checking. And again, this is almost identical to the data sets that are used in the M800. Now, number 6 there is the telemetry monitor data set. This is a data set that will only function if you have the telemetry monitor upgrade selected, and the purpose of this is to give you this remote monitoring capability. So you'll find that these are transmitting data whether or not there is an upgrade, but if you don't have the upgrade installed, your telemetry monitor system will not work with this data. Okay, now our later ECUs, the 100 series ECUs, it's not possible to do setup work here using an RS232 connection. These devices only allow setup via the CAN bus, and this is normally using our UTC device, which is our USB to CAN device. So if you have one of these ECUs, you don't need to concern yourself with RS232 in terms of how the ECU manager program works. It's more to do with transmitting data from device to device. So in the case of these ECUs, we have the similar data sets to the ones on our earlier ECUs, such as the M48. And in this case, they are data sets 1, 2, and 3, as you can see on this list below. Once again, this is effectively the same as those 5, 6, and 7 sets on the earlier ECUs. The third one uses CRC32, which is a better error correction mechanism. The second one is our telemetry setting, and the first one is our normal dash-logger data set. And again, there's a baud rate setting here, or bits per second, and once again, it allows you to select the speed and the number of stop bits. Again, 19201 means it's 19,200 bits per second, and it's got one stop bit. Okay, so there's not really a lot more to add here. The only other thing that the M100 series adds is that we can have not only our standard data sets, we can also have custom data sets. Now these are transmitted in a number of formats, but effectively you can select in your M800 or M400 a smaller data set, just transmitting the particular information you're after. And this is quite useful because the normal data sets do actually consume a lot of bytes, and therefore the repeat rate may not be sufficiently fast. If you're using a high telemetry baud rate and a small custom data set, you can get very high data rates. In an M800, we can also receive GPS data, and this is a predefined function, so there is no menu option here as to how that works. The only thing you can change is the data rate. The two GPSs that we commonly sell are either at 19,200 bits per second or 38,400 bits per second, so it's important that your telemetry baud rate is set to the same number. Okay, now dash loggers, there are a number of variants of these devices, and they have varying capabilities. The setup of our earlier dash loggers can be done via RS232, so the ADL, the SDL and the ADL2 can all be set up via RS232. The ADL3 and SDL3 dash devices can only be set up via either Ethernet or USB. I beg your pardon, only via Ethernet as a matter of fact. But the earlier dashes you can either use USB or serial. So if you're in the ADL dash manager and you want to set up a serial connection, you use the Tools menu option and you go Tools, Connection Settings, and then you click on Add and you add a serial connection. So you can see here in our serial settings, we've clicked on this Add button, then it opens up a serial connection dialog, which you can see here. We must give it a name. We must define how it's going to work, and this does allow a certain number of modem settings, but normally we just connect directly to a COM port, and we set our baud rate, our flow control, and we can define the dash serial number, and then we click OK, and then you can see here on the left we have an option for serial communications. Now in our dash manager programs, one of these options will be checked, and that's the one that's going to be active. So if you set up a serial connection and you don't click on the Make Active button, it will still be trying to use the USB or the CAN. So when you bring that menu up, just make sure it actually is selected here, and you can see that little tick there. That's pretty straightforward. Okay, now as we said, RS232 can't be used for setups with our later dash devices, that they use Ethernet. And when you want to use these devices to get data from ECUs, the simplest way is to use the templates that are pre-packaged with our dash programs. Now these templates include those data sets that we saw earlier with the M800 and so forth, and so you simply open the communications menu, you bring in the RS232 message, and you select one of those M800 or so forth data sets, and really that's all you need to do. It's very straightforward. Certainly the quickest way. If you've set up a custom data set in one of the ECUs, then you can define that manually if you like, and normally with M800 ECUs you can actually save a custom data set as a template also, and that just means you can bring that in equally quickly. Now the other thing is that a lot of people use our dashes of course with other devices, and many of these devices transmit on RS232, and in our Dash Manager software we have incorporated as many of these devices as we can. So you can acquire information from many other brands of ECU or dashboard just by selecting the correct option. Now if you find there's something where you don't have particular data and it's not available as a selection, you should contact MoTeC support and we will attempt to resolve that for you. Okay, now we'll have a quick look at the PLM. The PLM is one of the devices where RS232 is the only way you can communicate for setup. PLMs will transmit data on CAN, which means they can be used, for example, with a dash logger and transmit CAN data, but the CAN port is not used for the setup. People do have a little bit of trouble with PLMs using the USB to RS232 adapter cables. In some cases you just plug in and it works, and in some cases you have trouble establishing communications. So firstly, if you try to get the configuration from the device and you see this message here, it's because you either don't have the COM port connected or the device is not actually turned on. So the first thing it will do is look at the COM port you've selected and wait. It sends out a request and then it waits to see if there's any data coming back from the PLM. It's quite a long timeout. I think it's about 5 or 10 seconds. And if you don't get anything in that time, it'll show you this message. So then, therefore, you may need to go into the options menu and just simply go Options, Communications Port. And you can see here on the right, we've selected the port number. And of course, you need to select the port that corresponds to either your physical COM port or to your USB to RS232 adapter. Once again, you need to select a COM port in the range of 1 to 8. So if you have plugged in a USB adapter, you should make sure that it is pre-allocated to one of those COM port numbers. Now, if you have still difficulty communicating when you're trying to get a configuration, from time to time, one option is you actually unplug the PLM from the serial adapter. By that I mean you leave the USB to RS232 part of the cable plugged into your laptop. You unplug the PLM, then you press the Get Configuration selection in the program, then you plug in the PLM. Now this just it sounds a little bit silly, but in some cases this allows the thing to connect better. Once it's made that connection, it's quite easy to change your settings and send them back to the PLM. So this just can be a problem with the initial connection to these devices. Okay, now there's a fairly extensive bunch of problems people experience with our telemetry monitor program, and so normally if people are having trouble, we like to go through a fairly straightforward sequence. The objective here is to firstly check that the telemetry system is working without a radio link, and then to move it to a radio link. Now, just a reminder that if you set your ECU to the telemetry type of data set, it will transmit data, but it will not necessarily be received in the telemetry monitor program unless you've got the telemetry upgrade in your ECU. So there will still be data, but it's coded data, and if the upgrade has not been enabled in the ECU, although it will be transmitting data that you can actually see with a monitoring program, the monitor software will not function. So what we like to do is, firstly, we'll set up our ECU, turn on our telemetry data set, and we'll just make a hardwired connection straight into the laptop via a normal RS232 cable, and if necessary via our USB to RS232 adapter. And what this does is allow us to make sure that all of our communication settings are correct, for example our baud rate and so forth, whether we've got our flow control turned on or off, and we should of course be able to see the telemetry monitor working correctly when all of these settings are correct. And if you can't make it work on a cable, you're never going to get it to work on a radio link. So, firstly, we open up our settings, communications and data source option in our telemetry monitor program, and we use that to check our port setup. So you can see here, it's a little bit hard to see, but we've got COM1 selected here, and if that's not the COM port we're going to use, we click on this configure button here, and that will open this dialog over here. And so here is where we set our bits per second rate, various other things like parity, stop bits, and our flow control. And again, we would suggest you have flow control set to none for your initial setup. There are some radio systems that do require flow control, but generally speaking, setting that to none is your best starting position. So once we've set all those settings, we should be able to go into our telemetry monitor program, and then we can select the view option and show statistics, and what that does is open up this box in the bottom of our program, and here we can see whether there are COM port errors and what the general packet data statistics are. So this is a very simple way to make sure that everything's working. Now you can see in this example, for a start, I have all of my ECU data. This is just from an M800, and I've got live data, so clearly my telemetry link is working. And if you look in this COM port errors frame, you'll see that there are 0 errors because we've just basically got a hardwired connection. All of our settings are correct, and that's what we'd expect to see. This is, in other words, a good link. Now, on the left, in the statistics box, you can see there are some bad characters, a smallish number, and that means that we've had some bad packets of data. Once again, this relates to the fact that each message contains a large number of characters, and if the error correction within the telemetry monitor program sees some character errors, it'll reject that packet of data. Generally speaking, this has been running for a few minutes. We've got several thousand OK packets and something like 800,000 characters, and we've got some bad characters, and therefore we've got some bad packets. This may have just been a process of plugging and unplugging the cable, but in general terms, with none of these errors, that's the kind of thing we're wishing to see before we proceed to using a radio link. Okay, so the next thing we want to do is we will test that the two radio links talk to each other just using a data transmission terminal program. So I'm going to show you one of those a little bit later, but there are a few options here with the PC. Virtually all PCs have a program called Hyperterminal, which is just part of the normal operating system, and there's also a program called RealTerm that we also suggest. So what you need to do is get two laptops, if you like, plug each laptop into one of your radios and use one of these terminal programs to just type messages, because if there's any corruption of the radio data, then you won't even be able to transmit typed messages. And once again, if your telemetry system works correctly, but the radio system is making the data fuzzy, then you're not going to see valid data in your telemetry monitor program. So the two possibilities that can make these systems not work properly is either you've got too high a transmit speed and the radio system isn't capable of matching that speed, or you've set a transmit speed that is different to the speed that the radio system has been set up for. And in those cases, what you're going to see is the sort of frame or packet errors that we didn't see on the previous screen. Now, with our conventional radio modems, which are the older type of radio modems that MoTeC used to sell, we no longer sell them. These normally you just power them up, they transmit carrier, and as soon as they find carrier, they'll start connecting with data. So they're very straightforward. The current radio systems we sell, the spread spectrum modems, they work essentially the same way. We sell them predefined. As long as your data speed is correct out of your transmitting device, then these radio sets more or less work perfectly. You just make sure you use the car one in the car and the pit one in the pit. That's because one's a transmitter and one's a receiver, and they just get plugged in and they go. As soon as they see that there's carrier signal, they will connect, and that means there's no further interaction required. It's as close to plug and play as you can get with a radio system. The other form of radio system that gets used quite a bit are GSM modems, and these are ones that use the cellular telephone network. Now in this case, it's not quite so straightforward, because basically you've got to actually make a phone call to the car to set up the radio connection. So you use the laptop to dial the car via the GSM modem, and then once that connection is available, your data stream will start to function. Now, just to make sure this works, you can use a laptop just to dial your own cell phone, and that way you know that your GSM modem is actually dialing out. That's a pretty straightforward test. Okay, now the last category here would be radio systems that aren't supplied by MoTeC, and in this case it's very difficult for us to give you detailed help. Firstly, it's important that you have your flow control set up correctly. Again, we suggest you start with no flow control, but in the case of some radio systems, if they're not capable of keeping up with the data speed, then they may require flow control. Most radio systems that have these flow control options, they use the Hayes AT command set, which is a command set used for all telecommunications modems, and it goes back to the early days of low-speed telephone modems, but it's used in most radio systems as well. Normally you would need to refer to the manual for the individual device to do the setup here. And what happens is you use AT commands via a terminal program to set, for example, your speeds. You issue those commands to the modem, and then you use an AT command to save or store these settings so that the next time the device powers up, it'll just default to those settings. Again, this really relates to individual systems, And if needless to say, that's why we recommend our own systems, because our engineers have tested them and installed them in a fashion that means you can just plug and play, hopefully. Okay, now just a quick look at some of the tools I've mentioned. The first one is a simple terminal program. It's very handy if you've got a RS232 link coming out of an ECU. You just plug it into your USB to serial adapter, and with something like a hyperterminal or realterm, you can see the data. And this allows you to confirm that your baud rate or your bits per second is correct, and that the transmitting device is actually producing useful data. Now, the inbuilt terminal program is called hyperterminal, and that's how you find it. You go through the start menu, and that's a fairly simple program, and it's not one we tend to use. The one we suggest is called realterm. It's a free download from SourceForge. There's the link, and that's what you can see on screen is an example of realterm, and that's actually showing us dataset 1 out of an M800. Okay, so in this case, what we're looking at is we're looking at hexadecimal values. I'm not going to go into the details of how hexadecimal works. There are other webinars on that topic, but the point here is that as you run the ECU into the laptop, this data will be continuously updating, and this will scroll the data as new data comes in. And down here you can see the amount of data that's been received and the characters per second. At the moment, I would say that's because the ECU's been turned off. So normally this would be showing you exactly how many characters it's received, and you may recall that the characters per second is a divided number which is based on the bits per second approximately divided by 10. So if this port was running at 19,200 and we're running basically a normal data stream out of an M800, we would expect to see roughly 1,900 characters per second at maximum. So this is a useful tool just to establish the veracity of your data before you plug it into the other device that you may be looking at. Now, you should recall that most RS232 systems only allow a single receive device, especially within the PC domain, and therefore if you're running, for example, this realterm program, you can't open our telemetry monitor and access the same port. Only one PC program can access that serial port at a time. So we may use this program first to see that we're getting our serial data, and then we'll close this program and we'll open our telemetry monitor, which will open the same port. There are some occasions where programs don't properly shut the ports, and when you open another program you see an error, and to be honest, the simplest way to get around that is to close all the programs, reboot the PC, and then launch the program that you actually need to access the port. So in some cases, access to RS232 or COM ports can be slightly clunky, and just reboot the machine. Now, another quite a useful tool is a GPS generator. This one has quite a lot of options. There's a free download and there's also a paid download. And what this will do is generate GPS data. I'll just slip back slightly. If we go back to this program here, there's actually a capture option here on this tab, and this allows you to record this data that's coming in. And there's also a send option, and you can use this send option to play back a GPS file. This is a very useful thing to do. So for example, you can use your GPS generator program, which is the one I've just showed you here, and this will generate a GPS transmit data file, and then you can use realterm to send this file, for example, to an M800 or to a dash logger, and to verify that the GPS receive function is working properly. Again, this is something we frequently do here. It's not always possible to test a live GPS device, so we can just send a pre-recorded GPS message string out of realterm, and our ECU or our dash will show GPS data as if it's live data. So back to this one, this is the one that can be used to generate that sort of data. Very useful program. There are a number of things you can change, the originating GPS location and so forth. It's not a terribly sophisticated program, but it does generate properly configured GPS data. So yeah, once again, quite a useful thing. Now, another tool that may be considered high-end, and this is a very inexpensive option compared to, for example, an oscilloscope. What this is a logic analyzer, which includes serial decoding. And you can see in the red circle, I have this is like a scope display. but it's much cheaper than an oscilloscope. It simply runs on a USB port on a laptop, and this device is available for about $160 US. It's a very useful device. So you can use this to probe serial data, and you can select what type of data is going into this channel, and if you tell it it's serial data, it will actually show you the data value here. So that shows you what we have here. This is our idle condition. This is our start bit here, and then these are our data bits. Okay, and then it's in very small print, but what you can see there is actually the hexadecimal value of that data byte. So this is a very, very handy program, and as I said, it's extremely inexpensive, and it's just generally quite a useful tool for looking at things like ref or sync patterns and so forth. You can look at all these things in this logic analyzer. It does have a few limitations. It's really only designed for 5-volt signaling. So what we normally do is we just use a 10K resistor between the probe and the data we're looking at. And in the case of something like RS232, that will just isolate the voltages and it won't blow this device up. So you can, for an inexpensive device, it's a very powerful tool. Okay, that's the end of our webinar. I apologise for the length, but I hope that there's been some useful information there for you. Now, of course, we have other webinars online. You can go to our MoTeC website and you can view any of these webinars anytime you like. And also we have our MoTeC web forums where both MoTeC staff and support staff and engineers and many of our customers and dealers participate. And there's a lot of answers there to questions you may have. So it's very worthwhile to have a look at our forums as well. Thank you again for attending. That's the end of this webinar.